The universe harbors a profound secret about its very nature. A truth so fundamental yet so counterintuitive that it challenges our most basic assumptions about existence. Deep within the fabric of reality lies an element so essential to our understanding of the cosmos that it might just reveal time itself to be an illusion. In 1905, when Albert Einstein published his special theory of relativity, he inadvertently began a scientific revolution that would ultimately question the reality of time itself. His equations showed something remarkable. Time is not absolute. It does not flow at the same rate for everyone, everywhere. This revelation was just the beginning of a journey that would lead physicists to question whether time exists at all in the way we intuitively understand it. Dr. Benjamin Blake, a theoretical physicist at the California Institute of Technology, has spent decades contemplating this question. When we dig deep into the fundamental structure of reality, he explains, we find that our conventional understanding of time begins to dissolve. The mathematics simply does not support the idea of time as an independently flowing river, carrying us from past to future. This is not mere philosophical speculation. The mathematics of modern physics, particularly quantum mechanics and attempts at quantum gravity, suggest that at the most fundamental level, time may be emergent rather than fundamental, a byproduct of more basic physical processes rather than a primary ingredient of reality. The key to understanding this lies in a concept that pervades all of physics: symmetry. Symmetries are transformations that leave something unchanged. When you rotate a perfect sphere, it looks the same. When you shift your position in empty space, the laws of physics remain identical. These symmetries are not just aesthetic curiosities. They are the hidden architecture of our physical theories, the scaffolding upon which our understanding of the universe is built. But there is one symmetry that stands above all others in its profound implications: CPT symmetry. CPT stands for charge, parity, and time reversal. This fundamental theorem in physics states that any physical process will occur identically if we simultaneously reverse the charge of all particles involved, mirror image the entire process, and reverse the direction of time. This symmetry is not broken by any known physical law. It appears to be absolute. What does this mean for time? It suggests something remarkable. At the fundamental level, the laws of physics do not distinguish between past and future. There is no arrow of time embedded in the basic equations that govern particles and forces. The distinction between past and future may be an illusion, a consequence of our macroscopic perspective rather than a fundamental feature of reality. Dr. Rachel Green, a quantum cosmologist at Princeton University, puts it succinctly: in the equations that describe the most fundamental processes in nature, time is treated differently than in our everyday experience. It is not a flowing river but more like a dimension, similar to the three dimensions of space, that simply exists with all points equally real. This view of time is called the block universe perspective, where past, present, and future all exist simultaneously. The apparent flow of time, the distinct feeling that the present moment is special and that the future is open while the past is fixed, may be nothing more than a psychological construct, a way our minds organize the four-dimensional reality in which we are embedded. The evidence for this counterintuitive perspective comes from multiple directions. Einstein's relativity demolished the notion of absolute simultaneity, the idea that everyone can agree on which events happen at the same time. Depending on your state of motion, events that appear simultaneous to one observer might occur in sequence to another. This means that the division of reality into past, present, and future is not absolute but relative to the observer. Quantum mechanics further complicates the picture. The famous delayed choice experiments, first proposed by John Wheeler in the 1970s and confirmed in numerous laboratories since, suggest that events in the present can seemingly influence the past. While interpretations vary, these experiments reveal that time at the quantum level behaves in ways that defy our classical intuitions. But perhaps the most compelling evidence comes from our attempts to reconcile quantum mechanics with gravity, the quest for a theory of quantum gravity. In every serious approach to this problem, from string theory to loop quantum gravity, time as a fundamental concept seems to disappear. Instead, what emerges is a more primitive notion from which our familiar experience of time must somehow be derived. This brings us to the heart of our story: entropy. If there is one element that explains why time might not be real, at least not in the way we typically conceive it. It is entropy. This concept, born in the study of thermodynamics in the 19th century, may hold the key to resolving the apparent contradiction between our experience of time's arrow and the timelessness suggested by our most fundamental physical theories. Entropy is commonly described as a measure of disorder or randomness in a system. But more precisely, it quantifies the number of possible microscopic arrangements that could give rise to the same macroscopic state. A deck of cards arranged by suit and number has low entropy. The same cards thoroughly shuffled have high entropy. The fundamental law governing entropy, the second law of thermodynamics, states that in an isolated system, entropy tends to increase over time. This law gives us the arrow of time that we experience. We remember the past and not the future because the past had lower entropy. We can break an egg easily but cannot unbreak it because the broken state has vastly higher entropy than the unbroken state. The flow of time as we experience it is intimately connected with this increase in entropy. Ludwig Boltzmann, the 19th century physicist who formalized much of our understanding of entropy, realized this connection. He proposed that the apparent arrow of time is entirely due to the statistical tendency of systems to evolve from less probable, lower entropy states to more probable, higher entropy states. The direction of time, in this view, is nothing more than the direction of increasing entropy. What is remarkable about this perspective is that it explains our experience of time's flow without requiring time to be fundamental. The laws of physics that govern the microscopic constituents of our world, atoms, electrons, quarks, are time-symmetric. They work equally well whether time runs forward or backward. Yet we experience a clear asymmetry. Entropy provides the link between these two seemingly contradictory facts. Dr. Blake has spent years exploring the implications of this idea. If you really follow the mathematics, he says, you find that time itself may emerge from more basic timeless physics. What we experience as the flow of time could be a consequence of how our brains and bodies process the increasing entropy of our environment. This perspective has received support from recent work in quantum information theory. Research by scientists like Sean Carroll at Caltech and Seth Lloyd at MIT suggests that quantum entanglement, the spooky connection between particles that Einstein once called spooky action at a distance, plays a crucial role in how entropy increases and, consequently, how we experience time. When quantum systems become entangled with their environment, a process called decoherence, information that was once localized becomes spread out and effectively inaccessible. This spreading of information appears to be intimately connected with the increase of entropy and the apparent flow of time. Quantum entanglement may be the missing link, explains Dr. Green. It provides a mechanism for how microscopic, time-symmetric processes can give rise to the macroscopic arrow of time that we experience. The direction of time could be nothing more than the direction in which quantum information spreads out and becomes more entangled. This brings us to a profound insight. Time may not be a fundamental feature of reality, but rather an emergent phenomenon, a consequence of how more basic, timeless processes unfold. The mathematics of these processes, described by the eternal laws of physics, exists outside of time. What we experience as the flow of time may be nothing more than our limited perspective on this timeless reality. To appreciate the full significance of this idea, we need to delve deeper into the history of how humans have conceptualized time. Our intuitive understanding of time has evolved significantly over the centuries, shaped by advances in both science and philosophy. In ancient cultures, time was often viewed cyclically. The Mayans, ancient Greeks, and many Asian civilizations saw time as a repeating pattern of seasons, celestial movements, and generations. The linear conception of time with a distinct past, present, and future became more prominent with the rise of Judeo-Christian thought, which introduced the idea of history as a directional progression from creation to apocalypse. Isaac Newton, in the 17th century, formalized the prevailing view of his era in his laws of motion and universal gravitation. In Newtonian physics, time is absolute and flows uniformly throughout the universe, independent of space or matter. This view aligned well with intuition. Time was a cosmic metronome, ticking at the same rate for all observers, regardless of their location or motion. This comfortable view was shattered by Einstein's theories of relativity in the early 20th century. Special relativity revealed that time dilates for objects in motion, clocks in motion run slower than stationary ones. General relativity showed that gravity affects the rate of time's passage. Clocks in stronger gravitational fields run slower than those in weaker fields. These effects are not mere theoretical curiosities. They are measurable phenomena that must be accounted for in technologies like GPS satellites. Einstein's work led to a new understanding of time as a dimension intertwined with space in a four-dimensional space-time. In this framework, time loses its special status as something that flows. Instead, it becomes more like another dimension of space, a direction in which events are arranged, not a dynamic process of becoming. Hermann Minkowski, Einstein's former teacher, articulated this view in 1908. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This block universe perspective received further support from the work of mathematician Kurt Gödel in the 1940s. Gödel discovered solutions to Einstein's field equations that contained closed time-like curves, paths through spacetime that return to their starting point in both space and time. In effect, these are time loops that would allow travel into one's own past. While such solutions might not describe our actual universe, they demonstrated that Einstein's equations are compatible with a view of time that completely contradicts our intuitive sense of past, present, and future as distinctly different. The quantum revolution of the early 20th century added yet another layer of complexity to our understanding of time. In quantum mechanics, particles exist in probability distributions rather than definite states until measured. This probabilistic nature seems to introduce an irreversible element to physics. Measurement collapses the wave function in a way that cannot be undone, seemingly introducing a preferred direction to time. However, the Schrödinger equation, the fundamental equation of quantum mechanics that describes how quantum states evolve, is itself time-symmetric. It works equally well whether time runs forward or backward. The apparent irreversibility of measurement, known as the collapse of the wave function, remains one of the most puzzling aspects of quantum theory and has spawned multiple interpretations about the nature of reality and time. In the 1960s, physicist Hugh Everett proposed the many-worlds interpretation of quantum mechanics, suggesting that each possible outcome of a quantum measurement occurs in a different world or branch of the universal wave function. In this view, the apparent collapse is simply our subjective experience of becoming entangled with one particular outcome. If correct, this would mean that all possible futures already exist in a vast, branching structure of reality, further undermining the notion of time as a linear progression. Julian Barbour, a British physicist who has spent decades studying the nature of time, has developed a radical perspective. In his theory of timeless physics, Barbour argues that time does not exist at a fundamental level. What we perceive as the flow of time is actually the relationship between different configurations of the universe, what he calls time capsules, that contain records of other configurations. These configurations exist in an abstract space called configuration space, and the relationships between them give rise to our experience of time without time itself being real. Each moment, what I call a now, is a complete, self-contained slice of the universe, explains Barbour. The illusion of time passing is created by the way these nows contain information about other nows. Our brains interpret this information as memories and anticipations, creating the subjective experience of time's flow. Barbour's ideas are not mere philosophical speculation. They emerge from attempts to formulate a quantum theory of gravity, the holy grail of theoretical physics that would unite Einstein's general relativity with quantum mechanics. In almost every approach to quantum gravity, from string theory to loop quantum gravity, time as a fundamental concept seems to disappear. This phenomenon is known as the problem of time in quantum gravity. When physicists try to quantize general relativity, they find that the resulting equations seem to describe a static reality, one in which nothing happens and nothing changes. This is the famous Wheeler-DeWitt equation, sometimes called the timeless Schrödinger equation, which notably lacks any reference to time evolution. Instead, it describes quantum states of the entire universe that are frozen, eternal. Carlo Rovelli, a prominent physicist working on loop quantum gravity, explains, "The disappearance of time is what we should expect when we put together what we have learned about the world from quantum mechanics and general relativity. The world is not a succession of events happening in a given order. It is a complex network of events where the notion of before and, after, loses universal significance. If time is not fundamental, how do we explain our powerful subjective experience of it? Why do we perceive a distinct past, present, and future if reality is, at its core, timeless? This brings us back to entropy, the element that may explain why time seems real to us even if it is not. Our brains and bodies are thermodynamic systems that process and store information. This information processing is subject to the same entropic constraints as any physical system. When we form memories, we are creating physical records of lower entropy states from our past. We cannot similarly remember the future because doing so would require the physically impossible task of recording higher entropy states in a lower entropy medium. Our experience of time is deeply tied to how information flows through our brains, says Dr. Green. Entropy constrains this flow to be unidirectional, creating our subjective sense of time's arrow even if the underlying physics is time-symmetric. Recent research in neuroscience supports this view. Our perception of time is not a direct reading of some cosmic clock but a construction of our brains. Various cognitive illusions, like the oddball effect, where novel stimuli seem to last longer than familiar ones, or the way time seems to slow down during life-threatening situations, reveal that our experience of time's passage is malleable and constructed rather than a direct perception of some external, flowing reality. This constructive nature of time perception has been demonstrated in laboratory settings. Experiments by neuroscientist David Eagleman at Stanford University have shown that our perception of time is intimately tied to the amount of information our brains process. When we experience novel or emotionally charged events, our brains create more detailed memories, making these events seem to have lasted longer in retrospect. Time, as we experience it subjectively, is largely a construction of the brain, explains Eagleman. It's a way for our minds to organize and make sense of the constant flood of sensory information we receive. The relationship between entropy and information provides another fascinating angle on this question. In the 1940s, mathematician Claude Shannon established information theory, showing that information and entropy are intimately connected. The entropy of a system can be understood as a measure of the information needed to specify its exact state. This connection between entropy and information has profound implications for our understanding of time. If entropy determines the direction of time, and entropy is fundamentally about information, then the arrow of time may be essentially informational in nature. The apparent flow from past to future might be nothing more than the statistical tendency for information to spread out and become less localized, a consequence of probability rather than a fundamental feature of reality. This perspective has gained support from work on quantum thermodynamics. Recent experiments have shown that the arrow of time can be effectively reversed in small quantum systems under carefully controlled conditions. By manipulating the distribution of information in a quantum system, researchers have been able to make entropy decrease locally, effectively running time backward for that system. While these experiments do not violate the second law of thermodynamics globally, they reveal the deep connection between information, entropy, and our experience of time's direction. The implications of these ideas extend far beyond physics, touching on profound questions of philosophy, consciousness, and even free will. If time is not fundamental, what does this mean for our sense of agency and choice? Philosopher of science Hugh Price argues that our notion of an open future, that we can influence through our choices, may be a misconception based on our time-bound perspective. In a block universe where all of time exists eternally, our decisions and their consequences are already determined. Not in the sense that some external force has decided them for us, but in the sense that they are fixed features of the four-dimensional spacetime. We tend to think of the past as fixed and the future as open to our influence, explains Price. But this asymmetry may be a projection of our perspective rather than a feature of reality itself. From a timeless standpoint, all events, past, present, and future, are equally real and equally determined. This view does not necessarily negate free will, but it does recontextualize it. Our decisions still matter. They are causal nodes in the network of reality that influence other events. But the sense that the future is specially open to our influence in a way that the past is not may be an illusion created by our entropy-bound perspective. The search for a theory of quantum gravity continues to yield insights into the nature of time. Loop quantum gravity, one of the leading approaches, suggests that spacetime itself is granular at the smallest scales, composed of discrete atoms of spacetime rather than being continuous. In this framework, time emerges from the relationships between these fundamental quanta of spacetime. String theory, another prominent approach to quantum gravity, replaces point-like particles with tiny vibrating strings as the fundamental constituents of reality. In some formulations of string theory, such as the ADS/CFT correspondence developed by Juan Meldacena in the late 1990s, time in our three-dimensional world may be emergent from a more fundamental, timeless reality described by a two-dimensional quantum field theory. These approaches, while different in their details, share a common feature. They suggest that time as we experience it is not fundamental but emerges from deeper principles. The exact mechanism of this emergence remains one of the great unsolved problems in theoretical physics. What makes this question so challenging is that time is not just a physical concept. It is deeply embedded in how we think about causality, existence, and consciousness itself. To say that time might not be real is not to deny our experiences but to suggest that those experiences might be explained in terms of more fundamental, timeless principles. Consider for a moment the radical implications of this perspective. If time is not fundamental, then the distinction between past, present, and future may be an artifact of our limited perspective rather than a fundamental feature of reality. All moments, what we call past and future, may exist simultaneously in a vast, four-dimensional structure that encompasses all of existence. In this view, the Big Bang is not the beginning of time but simply one boundary of our observable universe in the time dimension, similar to how the edge of our visual horizon is not the edge of space but simply the limit of what we can see from our particular location. The end of the universe, the distant future when entropy reaches its maximum and all energy has dissipated, would be another boundary, not a moment when time stops but simply the other temporal edge of our universe. Between these boundaries exists the entirety of cosmic history, with all moments equally real from the perspective of the block universe. Dr. Blake finds this perspective both scientifically compelling and personally meaningful. Understanding time as emergent rather than fundamental does not diminish the significance of our experiences, he says. If anything, it enriches them by connecting our subjective sense of time's passage to the deepest principles of physics. The quest to understand the true nature of time has practical implications as well. As we develop more sophisticated quantum technologies, from quantum computers to advanced gravitational wave detectors, our understanding of time's nature directly impacts how we design and interpret experiments. The development of quantum gravity theory might eventually lead to technologies that manipulate spacetime in ways we can barely imagine today. The search for a theory of quantum gravity has led physicists to explore increasingly abstract mathematical frameworks. One promising approach is causal set theory, developed by physicist Raphael Sorkin and others since the 1980s. This theory proposes that spacetime is fundamentally discrete and that the causal relationships between events, which event can influence which other events, are more fundamental than space or time themselves. In causal set theory, the universe is represented as a vast network of events with causal connections between them. Time emerges from the counting of these causal connections. The more causal steps between two events, the more time separates them. This approach naturally incorporates both the quantum discreteness of reality and the causal structure of relativity. Another framework that has gained attention is quantum causal histories, developed by physicist Fotini Markopoulos. This approach also emphasizes causal relationships over space and time themselves but incorporates quantum mechanics more directly. In this view, quantum systems evolve along multiple possible causal paths simultaneously, with our classical experience of time emerging through decoherence, the process by which quantum systems interact with their environment and lose their distinctly quantum properties. These approaches suggest a profound shift in how we understand reality. Rather than starting with space and time as the basic arena in which physics happens, they start with more primitive notions like information, causality, and quantum probability. Space and time emerge from these more fundamental concepts. The most promising approaches to quantum gravity all point in the same direction, notes Dr. Green. Time is not a primary ingredient of reality but emerges from deeper principles. The challenge is understanding exactly how this emergence occurs and reconciling it with our subjective experience of time's flow. The implications of time's potential unreality extend to cosmology as well. The Big Bang, often conceptualized as the beginning of time itself, takes on a different meaning in these frameworks. Rather than a moment of creation, it might represent a boundary condition, a point of minimum entropy from which our observable universe unfolds. The question of why the early universe had such extraordinarily low entropy remains one of the great unsolved problems in cosmology. Physicist Roger Penrose has proposed that the answer may lie in the nature of black holes and the eventual fate of the universe. His conformal cyclic cosmology suggests that the end state of one universe, when all matter has fallen into black holes and those black holes have evaporated through Hawking radiation, becomes mathematically equivalent to the Big Bang of a new universe. In this view, what we call the Big Bang might be connected to the end state of a previous cosmic epoch. Time, rather than beginning or ending, would cycle through these epochs, though cycle is perhaps misleading since each transition would involve a transformation of what we mean by time itself. These cosmological speculations remain at the frontier of physics, with limited experimental evidence to guide us. Yet they illustrate how deeply the question of time's nature is connected to our understanding of the universe as a whole. The problem of time in quantum gravity has led some physicists, like Carlo Rovelli, to propose a timeless formulation of quantum mechanics. In this approach, physical systems are described not in terms of how they evolve over time, but in terms of how different observables relate to each other. Time becomes a derived concept, emerging from the correlations between physical quantities rather than serving as an independent backdrop against which physics happens. We do not observe time, Rovelli explains. What we observe are physical variables, the position of the sun, the hands of a clock, our own biological rhythms. What we call time is a complex relationship between these observed changes. This perspective aligns with recent developments in quantum foundations. The field of quantum reconstruction attempts to derive the mathematical framework of quantum mechanics from simpler physical principles. Several of these approaches suggest that quantum theory can be formulated without reference to pre-existing space or time, with these concepts emerging from more basic quantum information principles. As we probe deeper into these questions, we find ourselves at the intersection of physics and philosophy. The nature of time touches on questions that have occupied thinkers for millennia. The relationship between being and becoming, the nature of change, the status of past and future events. Ancient philosopher Parmenides argued that reality is unchanging and that change is an illusion of our senses. In contrast, Heraclitus famously claimed that everything flows and nothing stands still, that change is the only constant. Modern physics suggests a synthesis of these views. The fundamental laws may be timeless and unchanging, as Parmenides thought, yet they give rise to the flowing, changing reality we experience, as Heraclitus observed. This synthesis points toward a profound truth. The timeless and the temporal may not be in conflict, but may represent different perspectives on the same underlying reality. The mathematician and philosopher Hermann Weyl captured this idea beautifully. The objective world simply is, it does not happen. Only to the gaze of my consciousness, crawling along the lifeline of my body, does a section of this world come to life as a fleeting image in space which continuously changes in time. This view suggests that consciousness itself may play a crucial role in our experience of time. Not in the sense that time is merely subjective, but in the sense that conscious observation may be integral to how timeless physical principles manifest as temporal experience. The relationship between consciousness and time brings us to another frontier of research, the neuroscience of temporal perception. Studies have shown that our brains do not process information in a continuous stream but in discrete chunks. Our perception of a smooth, flowing present moment is a construction. The brain collects information over intervals of roughly 80 milliseconds and synthesizes it into a coherent experience. Furthermore, what we experience as now is actually information from the recent past. It takes time for sensory information to travel from our sense organs to our brain and to be processed into conscious awareness. Different sensory systems operate at different speeds. Visual processing is slower than auditory processing, for example. Our brain compensates for these differences, creating a unified sense of the present moment from information that actually arrived at different times. These findings suggest that our subjective experience of time, the feeling of being in a present moment that moves forward, is largely a construction of our neural architecture rather than a direct perception of some external, flowing time. This aligns with the perspective from physics that time, as we commonly conceive it, may not be a fundamental feature of reality. Dr. Blake finds these connections between physics and neuroscience particularly fascinating. The convergence of evidence from such different fields, from quantum gravity to cognitive neuroscience, suggests we are on the right track. Time as we experience it may indeed be more about how our brains process information than about the fundamental structure of reality. If time is emergent rather than fundamental, and if our experience of its flow is a construction of our consciousness, what might this mean for how we understand our lives and our place in the universe? One implication is that the sharp distinction we draw between past, present, and future may be less absolute than we typically assume. The past does not cease to exist, nor is the future unreal until it becomes present. Rather, all moments may have equal ontological status, equal reality, in the complete four-dimensional structure of spacetime. This perspective does not mean that our actions and choices are meaningless. Rather, it situates them within a broader understanding of reality, one in which causality still operates but is embedded in a larger structure that encompasses all of time. The philosopher Immanuel Kant argued in the 18th century that space and time are not features of reality itself but are imposed by our minds as necessary conditions for experiencing the world. In a sense, modern physics has vindicated this view, suggesting that time as we experience it may indeed be more about our perspective than about reality itself. Yet unlike Kant, who saw space and time as unchangeable features of human cognition, modern science suggests that our understanding and experience of time can evolve. Through scientific inquiry and contemplation, we can develop perspectives that transcend our intuitive, time-bound view of reality. This broader perspective may have profound implications for how we think about mortality and the finite nature of human life. If all moments have equal reality in the timeless structure of spacetime, then nothing is ever truly lost. The moments of our lives remain eternally embedded in the fabric of reality, even after our biological processes have ceased. Understanding time as emergent can change how we relate to our finitude, reflects Dr. Green. The profound experiences of our lives, our connections, discoveries, moments of love and insight, are not erased by the passage of time but remain as indelible features of the complete space-time structure. This is not to suggest that death is an illusion or that our temporal experience is meaningless. Rather, it is to recognize that our intuitive understanding of time may capture only one aspect of a deeper reality, a reality in which all moments, including those of our lives, have a kind of permanence that transcends our everyday understanding of time. As we approach the frontiers of physics and cosmology, the question of time's nature becomes increasingly intertwined with the limits of human knowledge itself. How can we, as beings who experience reality temporally, fully comprehend a potentially timeless foundation of reality? This challenge has led some physicists to suggest that new forms of mathematics and even new modes of scientific thinking may be necessary to make progress. The hunt for a theory of quantum gravity continues, with approaches like string theory, loop quantum gravity, causal set theory, and asymptotic safety all providing different perspectives on the possible timeless foundations of reality. Each approach has its strengths and challenges, and it may be that the ultimate theory will synthesize insights from multiple frameworks. What seems increasingly clear is that time as we commonly understand it, as a universal, flowing medium in which events occur, may not survive in our most fundamental theories. Instead, it may emerge as a useful approximation, valid at the scales and energies of our everyday experience but not reflective of reality's deepest structure. This does not mean that our experience of time is an illusion in the sense of being unreal or unimportant. Rather, it suggests that this experience is a particular perspective on a reality that, viewed from a more fundamental level, may not be inherently temporal at all. The flow of time may be real in the same way that the solidity of a table is real, as an emergent property that arises from more fundamental processes, valid at certain scales but dissolving when we look closely enough. As we continue to explore the nature of reality, from the quantum realm to the cosmic scale, we may find that our understanding of time evolves as profoundly as our understanding of space did in the era of Einstein. Just as we now recognize that space is curved by mass and energy, we may come to see time not as an independent dimension flowing uniformly throughout the universe but as an emergent aspect of a more fundamental, possibly timeless reality. The element that may explain why time might not be real, entropy, connects our subjective experience to the deepest principles of physics. It provides a bridge between the time-symmetric laws that govern the microscopic world and the directional flow that characterizes our macroscopic experience. Through entropy, we may ultimately reconcile our powerful intuition of time's passage with the timeless mathematics that seems to underlie physical reality. This reconciliation does not diminish the significance of our temporal experience but enriches it by connecting it to the fundamental structure of the cosmos. Our subjective sense of time's flow, far from being an illusion to be dismissed, may be a window into how complex, conscious systems like ourselves engage with and emerge from the timeless foundations of reality. As we stand at the frontier of knowledge, peering into the mysteries of quantum gravity and cosmology, we may be approaching a revolutionary new understanding of time, one that transforms our conception of reality as profoundly as Einstein's theories did a century ago. In this emerging view, time may not be what we thought it was, but our journey to understand it connects us to the deepest mysteries and grandest structures of the cosmos. Perhaps the ultimate truth is that time, like consciousness itself, represents a frontier where our most sophisticated physics meets our most intimate experience, a boundary where objective description and subjective meaning converge. In exploring this frontier, we may discover not only the nature of time but also something profound about ourselves and our place in the universe. A universe that may be, at its deepest level, timeless yet infinitely rich in structure, meaning, and possibility.